Understanding scikit-learn's Kernel Ridge, a detailed explanation. Kernel Ridge is a powerful nonlinear regression model in scikit-learn that leverages the power of kernel methods to handle complex relationships between features and target variables. This guide will dive deep into the workings of Kernel Ridge, exploring its key components, strengths, weaknesses, and practical applications. What is Kernel Ridge regression? Kernel Ridge regression extends the familiar ridge regression by introducing kernels. Ridge regression performs linear regression while penalizing the size of the regression coefficients. Kernel methods, on the other hand, allow us to implicitly map the data into a high-dimensional feature space, capturing nonlinear relationships. Kernel Ridge combines these techniques to achieve both linear and nonlinear modeling capabilities. Key concepts. Kernels are functions that measure similarity between data points. Common examples include linear kernel simple dot product, useful for linearly separable data. Polynomial kernel captures polynomial relationships, allowing for complex nonlinear boundaries. Radial basis function RBF kernel measures the distance between data points. Commonly used for nonlinear regression. Regularization, a technique to prevent overfitting by adding a penalty term to the loss function. In Kernel Ridge, it penalizes the complexity of the model, preventing it from fitting the training data too closely and generalizing poorly to unseen data. How Kernel Ridge works. 1. Data transformation. The kernel function implicitly transforms the input data into a higher dimensional feature space. 2. Regularized least squares. In this higher dimensional space, Kernel Ridge solves a regularized least squares problem to find the optimal solution. 3. Prediction for new data points. The kernel function calculates similarities to the training data, allowing the model to predict the target variable. Benefits of using Kernel Ridge. Nonlinear modeling can handle complex relationships between features and target variables that linear models cannot capture. Regularization prevents overfitting and improves generalization performance. Flexibility. Various kernel functions can be used to tailor the model to the data characteristics. Potential drawbacks. Computational cost. Kernel methods can be computationally expensive, especially for large datasets. Hyperparameter tuning. Finding the optimal kernel and its parameters requires careful tuning. Interpretability. Kernel models can be less interpretable than linear models, making it harder to understand the relationships between features and predictions. Key values in YAML. YAML. Kernel function. Kernel RBF default. Use linear, poly, etc. Regularization parameter lambda. Alpha 1.0. Higher values increase regularization. Gamma parameter for RBF kernel. Gamma none, auto selected if none. Degree of polynomial kernel. Degree 3 default. Coefficient of the polynomial kernel. Core O1 default. Other parameters depending on kernel used. Detailed description of key values. Kernel specifies the type of kernel function to use. The choice depends on the data and the desired complexity of the model. Linear kernel dot product. Polynomial kernel. Degree specified by degree. RBF radial basis function. Kernel gamma specified by gamma. Other kernels might be available depending on the sklearn version. Alpha controls the regularization strength. Higher values imply stronger regularization, leading to smoother models that are less prone to overfitting but might underfit the data. Gamma, a parameter specific to the RBF kernel. It controls the width of the Gaussian kernel. Lower values create a wider kernel, capturing more global relationships, while higher values lead to a narrower kernel, focusing on local relationships. Degree specifies the degree of the polynomial kernel. Higher degrees allow for more complex relationships, but can lead to overfitting. Coa 0 a constant added to the polynomial kernel. It can adjust the influence of higher order terms. Application examples. Kernel Ridge is well suited for applications where nonlinear relationships exist between features and target variables. High-dimensional data is involved. Regularization is needed to prevent overfitting. Examples include predicting stock prices. Kernel Ridge can capture complex market trends and nonlinear patterns in stock price data. Image classification. Kernel methods can effectively learn intricate features from images, leading to high classification accuracy. Recommender systems. Kernel Ridge can help personalize recommendations by understanding user preferences and item characteristics. Choosing the right parameters. Kernel selection. Experiment with different kernels to find the best fit for your data. Regularization strength alpha. Start with a moderate value and adjust based on validation. Performance. Gamma if using the RBF kernel. Tune gamma using cross-validation. Conclusion. Kernel Ridge is a versatile and powerful tool for nonlinear regression. By understanding its workings, its benefits, and its potential limitations, you can leverage its capabilities for various data analysis tasks and achieve accurate predictions. Remember to carefully choose the appropriate kernel and tune the parameters for optimal performance.